Hello everyone, and welcome back to another lecture video. In this lecture video, we're going to be discussing the strain tensor, which is going to be perhaps one of the most critical things that we're going to have to deal with when looking at both the finite element method as well as general continuum or solid mechanics. So when we're looking at the strain tensor and want to derive the strain tensor, the first thing we're going to have to really discuss is configurations. And the first configuration is the reference configuration. Let's say that I had a potato in 3D space. You guys may be going, all right, great, Clayton, you got a potato. What can you do with it? Well, that's a great question. Right now, absolutely nothing. We need to provide some meaning to this potato in 3D space. How do we do that? Well, we can embed it into R3 or 3D space as a collection of material particles. So what I'm going to do is I'm going to take my potato and define it as a collection of particles. Now you guys may be saying, all right, Clayton, well, you had a potato which was meaningless, and now you just have a spotted potato, which is equally meaningless, and I would agree with you. So the question is, how can we provide some more mathematical and physical meaning to this potato? Well, we do that by introducing a coordinate system. So as you guys remember, orthonormal basis sets from linear algebra, well, that's what we're going to do here by bringing in a 3D coordinate system consisting of the orthonormal basis set E1, E2, and E3. From there, we can actually create vectors that will go from the origin of our coordinate system to points along the potato. So each material point on this potato is represented by a unique vector, which we're going to call big X in the space. So if I were to look at one of these vectors, it's simply going to be a linear combination of the basis set vectors. So any vector big X can simply be big X1 times E1 plus big X2 times E2 plus big X3 times E3. Now again, we have many points on this potato, and the collection of vectors corresponding to those material points is actually called the reference configuration, and we denote this collection of vectors as omega naught. Right, so this is going to be the reference configuration. This is basically our object embedded into 3D space before we do any sort of deformation or rotation or anything like that. Now, this leads us to the second configuration, which is called the deformed configuration. So right now, as we can see in our picture, we basically have our potato. It's in omega naught, meaning it's in the reference configuration, so before any deformation. And we have a point on this potato, which can be represented by a vector big X. Now, the goal of this course, as you guys probably know already, is we want to deal with these objects after deformation. So what we're going to do is we're going to take our potato and we are going to deform it by a deformation function f. Now, after we deform this potato, it is no longer in the reference configuration. It is now in what we call the deformed configuration, which we denote as simply omega, which is very simple. We go from omega naught, the reference, to omega, which is the deformed. Now, the key thing to keep in mind here is that once we start translating this potato and stretching this potato, that blue point in the reference configuration has now shifted. So what we're going to look at now is trying to figure out, okay, how can I create a nice relationship between the blue point in the reference configuration and the blue point in the deformed configuration? So one of the key things that we're going to have to look at is that linear map that went from our reference configuration over to our deformed configuration. So that linear map F is going to be bijective, aka invertible, it's going to be continuous, and it's going to be smooth and differentiable. These are going to be kind of the key things that we're going to look at here in the strain tensor aspect of this course. All right, now that we know that, we can also say, well, if I had a vector that went from the origin to the point in the reference configuration, well, I can also have a vector that goes from the origin to the point in the deformed configuration. All right, so this purple here is the path line of the particles is a vector function of the reference configuration. So this is why I said big X before, because now we're introducing a second vector, which I call small x. So if we're looking at big X, it goes from basically the origin to any point in the reference configuration. And if I look at small x, it goes from the origin to the point in the deformed configuration. And this small x here is called our position function, which is small x, and it's going to be a function of big X. Right, so that's going to be our position function. But now we can also create a second function, which we call a displacement function. So we can define a second vector function that relates the displacement of the particle in the current position to the reference position. So if we look at our two vectors already, the green and the purple, they both relate the points to the origin. Now I can create a third vector, which I'm going to call u of x, or a displacement function, which relates the displacement of the 2 points from one another. So it doesn't go to the origin, it's just directly from the point in the reference configuration to the point in the deformed configuration. And this vector function is called the displacement function, which is u of x. Now, if we look at this and take a step back and say, all right, well, this is actually just a triangle. We have big X, small x, and u of x. Well, that's just a triangle, so therefore we can do the laws of vector addition, and we can create a relationship between our position function small x and our displacement function u, where u is simply equal to small x minus big X. And that relationship right there, it's going to be one of the key fundamentals in all of our proofs going forward. All right, so before we start discussing the complexities of strain, let's go into something more simplistic, which is rigid body motion. So when we're talking about rigid body motion, there's actually kind of three subsections we can talk about. The first one is called rigid body displacement. And in this case, our position function, small x, is going to be equal to big X plus c. Now that c there might throw you guys off. Clayton, what is c? Well, c is simply just a constant vector. Therefore, if I know my position function, small x right here, I can calculate my displacement function, u. Because again, from the previous slide, we've concluded that u is equal to small x minus big X. So it's basically big X plus c minus big X, while we end up with just c. This means that every point in our reference configuration is now translated by a constant value c. Well, what does this look like? Let's say that we had a plate in 2D space, and we were to translate every one of the points on that plate by a constant value. We might end up with something like this. So of course the plate has been translated, but note that the plate has not been stretched or compressed or anything like that, and the plate has not rotated. So this is just a simple translation. All right, so the next one we look at is what we call rigid body rotation. And in this case, our position function is equal to q times big X. And in this case, q is a rotation matrix. So we discussed these before in our linear algebra review. Now that we know what q is, we can very simply find our displacement function u, which again is simply going to be small x minus big X. Therefore, our displacement function is going to be q minus I times big X. Now, what does this look like? Well, again, let's say that we have a nice plate in 2D space, and we were to apply a rigid body rotation. Well, we just simply rotate this plate. Now, a couple things to note. One, again, the plate has not been stretched, it has not been compressed, anything like that, so there's no strains yet at this point. And in this particular example, the plate has not translated. It was simply just rotated about the origin. All right, nothing too special there. Now, the third type, which you guys may have already guessed, is going to be a combination of 1 and 2, and that's what we call rigid body motion, which is going to be a combination of translation as well as rotation. So, of course, our position function is going to be qx plus c. Therefore, we can find our displacement function as simply small x minus big X, which leads us to q minus I times big X plus c. If we were to look at this, we have our plate here, and we were to apply this sort of rigid body motion, well, we may end up with something like this, where we see that the plate has been rotated and then translated. Or if you guys want to say it's been translated and then rotated. So nothing too crazy there. The key takeaway here when we're talking about these rigid body motions or displacements is that the plate does not stretch or compress or anything like that. It remains this exact same shape, and because of that, it actually has no strains. So that's kind of the little note here. Please keep in mind that the relative distance in these particular examples between the particles, it remains constant, therefore no strains. Now let's talk about something that would induce strains. So the simplest example is uniform extension or contraction. So we can actually characterize this uniform extension or contraction by three positive parameters, K1, K2, and K3. What does this look like? Well, if we were to look at a position function, small x, which is simply x1, x2, and x3, all we need to do is multiply our vector big X, so big X1, big X2, big X3, by a matrix consisting of diagonal components K1, K2, and K3, and this leads our position function to simply be K1 times big X1, K2 times big X2, and K3 times big X3. And just like before, what we did with rigid body motion is once we know the position function, we can then find our displacement function. So u, of course, is going to be equal to small x minus big X, which is equal to k1 minus 1 times x1, k2 minus 1 times x2, and k3 minus 1 times x3. Now, if you guys look at this, you say, all right, Clayton, well, the math looks all pretty and sexy, but what does it actually look like in real life? Well, let's say that we had our plates again in 2D space, and we were to play with some of these parameters. So the first case we're going to look at is when k1 and k2 are both greater than 1. So if k1 and k2 are greater than 1, this shows an extension. So it's being pulled in that direction. So k1, of course, refers to the vertical direction e1, or sorry, the horizontal direction e1, and k2 refers to the vertical direction e2. And if they're both greater than 1, well, therefore, it is extending in both of those directions. So now what I'm going to do to illustrate the playing with these parameters is we're going to keep k2 greater than 1, and we're going to play with the horizontal direction k1. So right now it's extended, meaning k1 is greater than 1. Well, if I were to set k1 is equal to 1, then we can see that there's actually no change in length in that horizontal direction. And as you guys may have guessed, if I were to take k1 as less than 1 but greater than 0, we can see that instead of extension, it is now being contracted or compressed in that direction. So we basically have three scenarios. First is contraction, where k is between 0 and 1. We have expansion, where k is greater than 1. And we have a third one where there's no change in length, which means that k is actually equal to 1. Now you guys may be saying, Clayton, hold on. I see that you have everything above 0, but what happens if k is actually equal to 0 or less than 0? Well, mathematically, it is possible. But what this represents is that the object itself basically becomes inside out. It inverts upon itself, as we can see in the picture here, which, although mathematically is possible, again, all you would have to do is set a negative value for k, it's not physically possible. An object cannot just invert upon itself. So this is why we basically have three scenarios if you guys want to if you guys want things to actually behave realistically. If you guys don't really care about that and you guys want your buildings to invert upon themselves, by all means go ahead. But for this particular course, we're going to be focused mainly on things that are physically possible. All right, so again, this was probably the most easiest example, uniform extension and contraction. But we have a second one, which is shear. Now, you guys have all heard of shear, but what does shear really look like when we're dealing with continuums? Well, we actually have two types. The first is simple shear. So in this case, our position function, which is small x, is going to be a diagonal rows of ones, so meaning that there is no expansion or contraction, or uniform expansion and contraction along those lengths, but we see an off-diagonal component as tan of theta. All right, so from this we can calculate our displacement function u, which is small x minus big X, and what we end up with getting is that the displacement function in the horizontal direction is actually going to be a function of the vertical position. So we see that we have an x2 in the u1. All right, what does this mean? Well, if we have our plate in 2 dimensions and we were to apply this sort of displacement field, we'd get something like this, that the further up we go vertically along this plate, the more it's going to translate horizontally. All right, so this is what we call shear, and this is perhaps one of the most common things you guys may have seen when we're dealing with our finite elements. You're going to get that kind of distortion. All right, so that's simple shear, but we also have something called pure shear. And basically, instead of having our theta represented in only a single entry of our position function, we actually have it in both sides. Now, what happens to this is when we get our displacement function, we see that our displacement function u1 is going to be a function of big X2, and our displacement function u2 is going to be a function of big 1. So if we were to look at this and we had our plate and we were to apply pure shear to it, we are going to get something that looks like this. So something you guys may have seen before, maybe not, but now that you guys can visualize it, hopefully it makes more sense. All right, so now that we're done talking about basically displacement field, you guys have a good idea of what the position functions and what the displacement functions are used for. We're going to get into the fun of this lecture. So of course you guys didn't click on this to learn about displacement functions. You guys clicked on this to learn about strains. Let's talk about strains. If we were to look right here, we have basically what we derived before, where we have our potato on the left in the reference configuration, and we have our potato on the right in the deformed configuration. We had two vectors, x and small x, relating the positions of our 2 points on these potatoes to the origin, and then we had a third vector u relating the displacement of the 2 points. So now when we're going to talk about strains, what we're going to do is we're going to introduce 2 additional points. On the left-hand side in the reference configuration, we're going to have a second point, which is light blue, and it is going to be at a distance dx from our original point. Similarly, on the other side, we're going to introduce the second point, which again is the same point in the reference configuration, and in the deformed configuration, it is at a distance d small x. Now, as you guys can imagine, having a big X and a small x is going to get really, really confusing. So what I'm going to do is every time there's a small x, I'm going to say small x. But if it's big X, I'm just going to say x. So if I say x, it refers to big X. If I say small x, it refers to small x. All right. So if I were to look at the displacement function between this second point, well, it's going to be u of x plus dx. And from here, this is where all the proofs start to take place. So let's say that we have 2 points. The first one is O, which is located at the origin, and the second one is P, which is located at the second point in the deformed configuration. And let's say that we wanted to travel between the 2 points. Well, as we can see from our mini vectors, we have a bunch of different options. The first path that we could take to go from O to P consists of going up of x, then plus dx, and then plus u of x plus dx. All right, so it's kind of taken what looks to be the long way around, something like that. But then, of course, we can say, well, you know what? There seems to be a simpler path, path number 2, which is small x plus d of small x. All right, so we basically have two paths to go from O all the way to P. Now, by the rules of vector addition, these are actually equal, so we can equate these two paths. So we got small x plus d of small x is equal to x plus dx plus u of x plus dx. All right. Now what we're going to do is we're going to start manipulating this equation. But this equation right here forms the basis of trying to find our strain tensor. First thing we're going to do is we're going to take that small x on the left-hand side and we're going to move it over to the right-hand side. And because of that, we see that we have a small x on the right-hand side and we have a big X on the right-hand side. So it's going to look something like this. Now, I arranged it in a particular way because remember that if we have small x minus big X, well, that's actually just equal to our displacement function, u of x. So far right now we have d small x is equal to d big X, or d of x, plus u of x plus dx minus u of x. Now, I'm going to introduce something that might scare you guys a little. I'm going to look at this right here, this component of u of x plus dx minus u of x, and I'm going to combine that into one parameter called nabla u. So nabla is that upside down triangle, and u again is just our displacement function. So nabla u, that's all just one parameter. And this comes from vector calculus, so you guys may or may not have already seen what exactly this is, but don't worry, I'm going to introduce it more in the next slide. So pretend that you guys know what nabla u is. We're going to continue on. So from here, I can say, all right, well, I have a dx on both sides, so I can factor that out to get d small x is equal to I plus nabla u of dx. Now, I'm going to introduce a second relationship, which again, you guys may or may not know, but I'm going to introduce it in the next slide, so don't be too worried, and that is f, where f is called the deformation gradient, and it's equal to I plus nabla u. So I can substitute that in there, and I get d small x is equal to f times d big X. Now this is where all the strain functions start to happen, because if we think about it, the strain is going to be the change in length between 2 points before and after deformation. So if I have the vector dx, well, the norm of dx is actually going to be the length before deformation. If I have d small x, I can find the norm of d small x, and that's going to be the length after the deformation. So by this equation down here at the bottom, I basically have an expression that can help me relate the length between 2 points before deformation and the length between the 2 points after the deformation. That's where it comes from. But before we get into that, we need to cover the things that I just threw at you. So remember that I introduced two concepts at you. The first one was the displacement gradient, which I said was nabla u. Now, what is nabla u? Well, it's actually very simple to calculate. As u is a vector value function, the nabla u, which is the gradient of u, is simply going to be a tensor field, or basically, since u is a vector, then nablu is going to be a matrix. Now, what does this look like? Well, nablu is actually going to be the partial derivative of ui with respect to big xj. Now you look at that and say, all right, well, this looks pretty gross already because of the i's and j's. So if we do our Einstein convention, we can actually simplify this for if u is a three-dimensional vector, we can simplify this into the following. Now, you guys may look at this and say, well, Clayton, this looks absolutely disgusting. I want nothing to do with this, and I don't blame you. But it's actually really, really simple. And the way that it's simple is we look at the rows of this displacement gradient. If we look at the first row here, we can see that we're always taking the the displacement function u1. So the first row is basically the displacement function u1 with respect to big X1. That's going to be the first component. Then we take u1, differentiate with respect to big X2. There's the second component. And finally, we take u1, differentiate with respect to big X3. There's the third component. So that first row there, all we need is the displacement function u1. Similarly, we can go down the list. The second row there, it always takes the displacement function u2 and then differentiates it with respect to big X1, big X2, big X3. And finally, the third row, exact same thing where we're just dealing with the displacement function u3. So it's actually not too bad at all to calculate. Now, the second thing I threw at you guys was the deformation gradient f. Now, the deformation gradient f has a very nice relationship with the displacement gradient, where f is equal to I plus nablu, where I, of course, is that identity matrix. From there, we can simplify it out into the following. So I have my identity matrix, and then I have my matrix of nablu, and this actually simplifies into the following. So if we look at this, the formulation for this deformation gradient is exactly the same as the displacement gradient, but instead of taking the partial derivatives of the displacement functions u, we're taking the partial derivatives of the position functions small x. So therefore, this deformation gradient is simply the partial derivative of small xi with respect to big xj. So again, if we were to look at the displacement gradient nablu, it's going to be the gradient of the displacement functions. If we were to look at the deformation gradient f, this is going to be the gradient of the position functions. All right. So now that you guys know what these are, we can return back to what we were talking about and look at that equation again in a more sophisticated manner, if you will, trying to sound fancy. So let's examine that derived equation where we had d small x equal to f of dx. Now again, the one thing that we're trying to find is the change in length between those 2 points, because the change in length will tell us what exactly the strain is. So if we want the length of a vector, of course we take the norm of the vector. So what we're going to do is we're going to dot the equation above with itself. The reason why we do this is because on the left-hand side, we now have d small x dotted with d small x. Now remember that any vector dotted with itself is actually equal to the norm of the vector squared. So this equation above can actually be simplified into the norm of dx squared, which is equal to dx dotted with f transpose of f dx. All right, so on the left-hand side, we now have the norm of the vector after the deformation, basically the distance between those 2 points after deformation. And on the right-hand side, we have something that looks a little bit ugly. So the best way to show you guys what this is to show you guys a nice simple scenario. So the first thing we're going to do is we're going to say, all right, well, this f transpose of f, we're going to call that c. And we're going to call that the right Cauchy-Green deformation tensor. And because of this, we can actually start to derive some very nice properties. So the first one is, let's just say, I'm not saying that it is, but let's just say that c, which of course is equal to f transpose of f, let's say it's equal to I. Well, if that's the case, then we basically end up with dx dotted with dx, which is equal to the norm of dx squared. Now, if the distance between those 2 points do not change after deformation, therefore there's actually no strain. The length remained the exact same. Therefore, we have rigid body motion. So that, of course, is the case when c is equal to I. So because of that, we're going to actually go back to c, and we're going to use its actual definition of f transpose of f. And what we're going to do is we're going to expand out what we get, and we get the following, where c is equal to I plus nablu plus nablu transpose plus nablu transpose multiplied by nablu. Now, from above, we said that, well, if c is equal to I, This corresponds to rigid body motion, therefore there's no change in length because of this I. So that means that a change in length must actually be associated with these terms over here, and these terms are going to be the terms that form our strain tensor. All right, so we're now going to redefine that right Cauchy-Green deformation tensor as follows, where C is equal to I plus 2 times this green strain tensor. So that epsilon green, that's what we call the green strain tensor. So our green strain tensor is actually equal to 1/2 of nabla U plus nabla U transpose plus nabla U transpose multiplied by nabla U. All right. And again, we call this right here our green strain tensor, and this is going to be very important. So if you guys have an assignment, it may reference the green strain tensor, and this is what you guys are going to use. So therefore, our green strain tensor is simply 1/2 of nabla U plus transpose plus nabla U transpose multiplied by nabla U, and we can also write this into component form. So I can find the components of the green strain tensor using the following formula. Now, if we look at this tensor, it's actually very nice because a strain tensor here, it's only a function of nabla U. So once I calculate that displacement gradient nabla U, I can easily find my strain tensor. Now, it has some nice properties associated with it, and the first one, which is great, is that it is symmetric. So as we discussed, something is symmetric, it really helps with all of our calculations. Now, the second property is it's valid for finite deformations. So no matter what scenario you guys have, this tensor will work out for you. However, we're going to discuss something else, which is the small strain tensor. And it relates to that fact that we just talked about. So remember that the green strain tensor is valid for finite deformations. However, in most applications, we deal with small deformations. Now, again, I just want to emphasize this. This course right here is meant for civil engineers, or more directed towards civil engineering. Therefore, when we're dealing with buildings, we expect small deformations. If your building is going crazy and deforming a lot, well, that's typically not a good thing. So this is why we deal with mainly small deformations. Therefore, if we were to look at our green strain tensor, we can look at this final component here, this nabla U transpose multiplied by nabla U, and we could say, well, for small deformations, this component here, it's actually going to be much smaller than nabla U itself. Therefore, we can assume that that last component is actually equal to 0. And this new modified tensor over here, we call this the small or the infinitesimal strain tensor. Therefore, when we're dealing with applications in this course and we discuss the small strain tensor, well, the small strain tensor can be calculated as 1/2 of nabla U plus nabla U transpose. All right, so again, very simple. If we want to calculate the small strain tensor, all we need is nabla U. And to determine nabla U, all we need is our displacement function. So if we have our displacement functions, we basically have our small strain tensor. Now, if you guys want it in component form, it is as follows. And if we look at this and compare it to the green tensor, it's much more simple. So again, some quick properties of this. It is symmetric, but it is only valid for small deformations. But of course, in this civil applications course, the small deformation assumption will hold up just fine. So just a little recap again, I want to emphasize. In this video, we talked about position functions, and with position functions, we can then calculate displacement functions. With displacement functions, we can then calculate the displacement gradient, nabla U, and now we found out that with that displacement gradient, we can then calculate our small strain or our green strain tensor. All right, guys, so I know that there was a lot of proofs and stuff like that in this particular video. Don't worry about them too much. As long as you guys now know where the formula for the small strain tensor comes from and how to use the small strain tensor, you guys will be good to go. That concludes this particular lecture. Thank you guys so much for listening. I will see you guys in the next lecture video.